Hello students, my name is Sumit Sagar Hota. I am a PMRA PhD student at IIT Palakkad. Today we will discuss lecture 8 of the light discussion section. In these sections we will cover lecture 36 to lecture 40 by Professor Ashok Desai, IIT Kanpur, of the subject Introduction to Airbreathing and Propulsion by NPTEL. In this section we will see some of the MCQ, and at the end I will solve some problems. So first question, okay, the combustor dash pollutants. Okay, combustors. Okay, so combustor, what is the work of a combustor? Combustor always decreases the pollutants. Okay, so that the fuel will completely burn. Okay, so inside the combustor we are always having idea to combust the fuel 100% or complete combustion of the fuel. Okay, so that's the reason why whatever the pollutants, especially carbon monoxide, okay, nitrous oxide, all these pollutants we have to combust inside this combustion chamber, so that near the exhaust or at the exhaust there won't be any kind of harmful pollutants which will affect the air pollutions, okay, which will affect the atmosphere and which causes the air pollution and health hazards. Okay, so that's the basic use of a combustor. The thriller is the dash part of the combustor. Okay, thriller always a first part of the combustor which induces the swirling motion and it helps in flame stabilization. Nitrogen oxides are released from what? Both combustor and burner, this can be released. Okay, it's a very few harmful pollutant. Okay. So the carbon monoxide pollutant released from the combustor is emitted during the dash process. Obviously, if you really going to see in carbon monoxide, one oxygen atom is there, that is actually oxidizer. Okay, so due to the oxidation process, these kinds of pollutants are emitted. Okay. Nitrogen oxides are produced during the combustion zone. That's truth. Okay. During the combustion only these nitrous oxides are formed. Not only nitrous oxide, if the fuel having nitrogen content, the nitrous oxide formation is there, and also if it is having carbon content, so it's the carbon monoxide formation is also there. Okay. When afterburners are not used in the jet engines, they are okay. Afterburner, where these afterburners are placed. So if you know that location, then this answer will be easy. Okay, so the afterburners, the name as the name suggests, the after the burner, these afterburners are placed. Okay, after whatever the combustion happened, everything will be over, then to again to reuse the exhaust gases, these afterburners are used. Okay, so that means it will reuse the exhaust gases. Okay, and what is the nature of exhaust gas? The exhaust gas is always a dry gas. Okay, so that's the reason why the when the afterburners are not used in the jet engines, they are what? Okay, dry. Okay, but here the question is something different. Okay, when the afterburners are not used in the jet engines, they are what? Okay, okay, so that means when a afterburner is going to use, okay, what it will do, the exhaust gases are already dry. After the combustion, the whatever the exhaust gases will come, that's already dry. So what I now told you what is the work of afterburner. Afterburner again dry the what, whatever the gas it's there. Okay, that's the reason why these afterburners are not going to be used in the jet engines, which is already mentioned in the question. When afterburners are not used in the jet engine, that means in the question they are telling the jet engines, the afterburners are not used, then what is the reason behind it? Because the afterburner will dry the whatever the dry exhaust gas exited from the jet engines. Okay, the answer will be dry, B. Okay, so the afterburners are not equipped with the with case of with case and liner. Okay, that's absolutely a false statement. The afterburner, there is actually a case, one case is required and one liner mechanism is also required. Okay, this is just a kind of afterburners internal parts, how these afterburners are designed, what and how it will reuse the things. Okay, so it will there will require a case, okay, or the outer cover and one liner mechanisms are required so that we can again reuse these exhaust gases. Okay, afterburners have dash rise in temperature than combustor. Obviously afterburner are in the what, so to answer this question, uh, what is the use of afterburner or what the afterburner exactly does, answer this question. Okay, so afterburner, what it will do, whatever the gas is, the gas came, it will actually add some of the air, okay, with the whatever the exhaust gases, because the exhaust gases having some amount of fuel which again going to burn because of the presence of oxidizer, and due to which whatever the temperature of exhaust gas, that's going to what, rise. Okay, and that's the reason why near the exhaust, the if a combustor with a afterburner having higher temperature than a combustor without a afterburner. Okay, so, that's the reason why afterburner is having high rise in temperature than a what, combustor. Okay. Okay, so the mixing of the fuel takes place efficiently in gas, okay, in afterburner, but it's a true statement or false? Okay, so afterburner there is no mixing happening. Okay, the mixing always happens in the combustor. Okay, it is actually reuse the whatever the exhaust fuel. Okay, so mixing of the fuel always happens in the what? Combustor. Okay, so it is a false statement. So now the afterburners require gas. Okay, so afterburner requires always what is there in near the exhaust? Always we need a flame holding mechanism so that it can hold the flame to maintain a what? Constant velocity of the flame. Okay. Okay, so now in this section we will solve two problems. Okay, two or three problems. Okay, so this is the first problem. So propane C3H8 is used as a fuel in an engine with 30% excess air. Assuming complete combustion, determine the composition of exhaust gases on the mass basis. Atomic weights are C equal to 12, O equal to 16, N equal to 14, H equal to 1. Molar ratio of the oxygen is 3.76. Molar ratio to oxygen is 3.76. Okay, so let's start the solution. Okay, so now here in this question they are asking 30% of excess air. Okay, and then what you need to determine the composition of exhaust gases. Okay, so let's start with the balancing case. Okay, what is the amount of what do you called what is the x, a, b and c? We just need to now find out so that our equation will be complete. Okay, okay, so here if you see in this question this written 30% excess air. Okay, so that means whatever the value we are find out, we have to again multiply it with that excess air of 13% in the what x value. Okay, so that's what the whole idea of this question. Okay, so let's start with the carbon balance. Okay, with carbon balance, if we can see here, A is equal to 3. Hydrogen balance, eight is equal to 2b, so b is equal to 4. Okay, so this is your oxygen balance. So 2x is equal to 2a plus b. So how 2x? X, if you see, x into O2. Okay, in the left hand side is equal to right hand side. Again in the CO2, 2 times a plus in water H2O, b times O. Okay, so yes, we solve it, we'll get 10. So here x is equal to 5. Okay, so now next let's go for the nitrogen balance. 2 times 3.76 times x is equal to 2c. 7.52 into 5, x we know already, 5 is equal to 2c, so c is equal to 18.8. okay, so just let's substitute all these values in the equation, and again we have to multiply with 1.3 because 30% excess fuel is required. Okay, it's operating in 30% excess fuel, so this, just first of all write down what is the thing we just find out now. Okay, so now you can see in the question it's written it's working with 30% excess fuel. Okay, so in the question says 30% excess fuel it's working, so those things we have to now consider. Okay, and so that again we have to find out the exhaust compositions. Okay, okay, so that's the reason why what I done. If there is excess air, what is the condition for excess air? There will be oxygen and nitrogen. Okay, so there will be some excess amount of oxygen and nitrogen will exist. Okay, so that's the reason why if you see in the previous part, all the balancing I done, we found also x equal to 5, but now we have to again do the oxygen balance and the nitrogen balance. Instead of B and C, we have to, what we have to do, C and 2 is replaced by now D times O2 and E times N2. Okay, because of excess air. Okay, so what will be now the new oxygen balance, how you can do? Okay, which is 1.3 times 5 is equal to, okay, left hand side oxygen 1.3 into 5, right hand side oxygen 3 into 2 in carbon dioxide plus 4 in water plus 2 times D. Okay, so solve it, we'll get D as 1.5. okay, so next we have to find out the E. So for E we have to again go for the nitrogen balance. Okay, so left hand side nitrogen 1.3 into 5 into 3.76 into 2 nitrogen atoms are there in one nitrogen molecule equal to 2 into E. So E will be your 24.44. okay, so now we can write down the final equation. C3H8 plus 1.3 into 5 times O2 plus 3.76 times N2 gives rise to 3 CO2 4 H2O plus 1.5 times what, O2, okay, and 24.44 times N2. okay, this is your final equation. So next what we will do the mass analysis. Okay, what is the total amount of mass? Okay. Sorry, the mass of now we will do the mass analysis. Sorry, the mass of CO2 3 times 12 plus 2 into 16 132 4 into 2 into 1 plus 16 72 m of O2 1.5 into 16 into 2 48 m times into 24.44 into 14 into 2 684.32. So what is the total mass? Is equal to 132 plus 72 plus 48 plus 684.32 is equal to 936.32 kg. Let it be. Okay, here you put everywhere kg per kilomole. Okay, kg per kilomole. Okay, kg per kilomole. kg per kilomole. kg per kilomole. And I don't. Okay, so yeah. So next we have to find out what product species mass fraction. Okay, very simple. Take the individual mass divided by total mass into 100. You can find out what is the percentage of mass used. Okay, so I of CO2, percentage of I of CO2, more specifically m of CO2, m total into 100, 132 divided by 936.32 into 100, which is 14.09%. Is your answer. Percentage of H2O, m of H2O, total mass into 100. Okay, so 72 936.32 into 100, 7.69%. Okay, So next question. Air enters a convergent nozzle from a reservoir of 2200 kilopascal and 100 degrees Celsius. If the exit area is 4 centimeter square, what is the maximum mass flow rate that this nozzle can handle? Assume the processes to be isentropic, that the air behaves as an ideal gas. Okay, so it's very simple question. Okay, so So gamma of air is equal to 1.4. Okay, next is here, take the ratio between the so we have to find out air enters at this. Okay, what we need to find out is what is the maximum mass flow rate that the nozzle can handle. Okay, that means we have to find out the m dot star, let it be, which is at the what exit of the combustor. Okay, we'll mark this point as okay, as what 0, and we'll mark this point as star. Okay, okay, 0 point and star point. Okay, in these 2 points we need to find out. Okay, so P star by P naught is equal to 2 by gamma plus 1 to the power gamma by gamma minus 1. So P star is equal to 2 by gamma plus 1 to the power gamma by gamma minus 1 into P naught. Okay, so what is a P star? P star is equal to, just put gamma as 1.4 because it's ideal gas and it's a air. Okay, so 1.4 plus 1 to the power 1.4 by 0.4 into 2200, because you see your P naught is what 2200. So PM from here we can calculate the P star value was 1162.22 kilopascal. Okay, now similar fashion we can find out T star. It's given its isentropic process, so we are actually applying the isentropic relation here as follows. So here I just find out the T star by using the isentropy relation between temperature and pressure. So now we have to find out what the sonic velocity, because these are the requirements to find out the m dot star. Okay. Okay, so one more requirement also there, that is density, that we'll later now find out. First we find out the sonic velocity. C star is equal to square root of gamma r T star 1.4 287 310.83. okay, so C star is equal to 353.4 meter per second. Okay, so yeah, next we find out the density. Is equal to P star by R T star. Okay, 1162.22 divided by 0.287 into 310.83. okay, so what is the value? This is your 13.02 kg per meter cube. Okay, so now actually substitute what is the m dot formula. M dot star is equal to rho star A C star. Okay, what is rho star? 38.02. and what is the area given in the question? What? 4 centimeter square. You are really going to see here it's written area is 4 centimeter square. So 4 into 10 to the power minus 4 meter square. Then what is the velocity? 353.4. okay, so what is the m dot star? 1.841 kg per second. This is the answer. Okay, so yes, so this is the next question. Okay, okay, so and okay. An open cycle gas turbine employs a regenerative arrangements. The air enters the compressor at 1 bar and 288 Kelvin and is compressed to a 10 bar with a compression efficiency of 85%. The air is heated in regenerator and then in combustion chamber till its temperature is raised to 1700 Kelvin, and during the process the pressure falls by 0.2 bar. The air is then expanded in the turbine and passes to regenerator, which has a 75% effectiveness and cause a pressure drop of 0.2 bar. The isentropic efficiency of the turbine is 86%. By sketching the gas turbine system and showing the process on the TS diagram, calculate the thermal efficiency and the power output if the mass flow rate is 100 kg per second. Take the mechanical and alternator efficiency as 98%. Cp of the gas 1.15 kJ per kg Kelvin and the Cp of the air 1.005 kJ per kg Kelvin. Okay, so first draw the TS diagram. Okay. So this is your diagram. This is your 2 point. This is your 1 point. This is your 2 dash. This distance is 9.8 bar given in the question. because the gas is compressed to a 10 bar. Okay, gas is compressed to 10 bar, that means 2 point is your what, 10 bar. Okay, so then during the process the pressure falls to what, 0.2 bar. So the whatever the pressure falls, okay, that's 0.2 bar pressure falls is there. Okay, so final pressure will be what, 9.8 bar. Okay, so next will be this. Three to 4 days. Figure 4. Again there is written that the air, okay, here also pressure drop is 0.2 bar. The region effectiveness and cause a pressure drop to 0.2 bar. Okay, okay, so after 2 there is a point we can rename. So this is 4 and 4 days. We already okay, so let this point be your y and this point will let it be your x. Okay, so let's start the solution. 1 to 2 days is the isentropic process. Just apply the isentropic relation. Okay, okay, so let's start the solution. Okay, so T2 dash by T1 is equal to P2 dash by P1 to the power gamma minus 1 by gamma. Okay, so what is a T2 dash? T2 dash is equal to T1. Okay, what is P2 dash by P1? Because P2 dash is your 10 and P1 is your 1, so 10 by 1. gamma minus 1 by gamma 0.4 by 1.4. T1 you will also know. T1 is your what? 288 Kelvin. If you solve it, you will get T2 dash as 556.04 Kelvin. Okay. So what is the isentropic of the efficiency of the compressor? Okay, given what compression efficiency is 85%. Okay. T2 dash minus T1 isentropic by actual. Okay, so what we need actually? We need actually T2 actual temperature at those two position. Okay, or more specifically at the compressor exit. Okay, so substitute the values, all the values we have. Compressor efficiency 0.85. the solve it will get 603.34 Kelvin. Okay, next we will see T4 dash by T3 means we have to apply the isentropic relation in the position 3 to 4 dash. Okay, we know what is the T3. The temperature in the combustion chamber rises to 1700 Kelvin. So which is the maximum temperature, which is 1700 Kelvin, because before the turbine what is there? Combustion chamber. Okay, so in the combustion chamber the temperature rises to the maximum value, then that same temperature is just to go to the what? Turbine. Okay. Just apply the what is called now if you really going to see it in the graph, this pressure is your P3. What is this P3 will be? Because 2.2 bar decrement is there. 10 minus 0.2, 10 minus 0.2, 9.8 bar. Okay. Similar way, so if you see here, the pressure drop by 0.2 bar. Okay, the air is then expanded in the turbine and passed to a regenerator 17 by some effectiveness something given. Okay, and it drops by 0.2 bar. Okay, okay, because you know very well whatever the pressure at the T1, that same will be there at the what? That pressure remains unchanged. Okay, so in the Y position what will be the pressure? Always it will be 1 bar. Okay, so in the question it's given that there is a 0.2 bar drop. Okay, from this to this in the question, this position, you know, this is equal to 1 bar, and this position they are telling the drop is 0.2 bar. Then what will be this pressure? As T4 dash. So T4 dash is equal to 1 plus 0.2, which is 1.2 bar. Okay, okay, so okay, So now just substitute, just again apply the isentropic formula between 4 dash and 3. Okay, so the real game is here we don't know what is the gamma value. Okay, because we have Cp of gas. Okay, in the question if you see the Cp of gas given but gamma didn't given, we have to find out the gamma first. Okay, so what is the Cp of the gas? Gamma r by gamma minus 1. Okay, which is 1.15, gamma r value 0.287 divided by gamma minus 1. When you solve it, we will get gamma as 1.33. Gamma of the gas more specifically you can write down. Okay, so let's find out the T4 dash then. Okay, then T4 dash is equal to 1700 is your T3, P2 dash is your 1.24 bar, this is your P3 9.8 bar, gamma minus 1 is your 1.3 minus 1, 1.33 minus 1, 0.33 by 1.33. When you solve it, will get T4 dash as 1009.6 Kelvin. This is the temperature exit of the what? Turbine. Okay, then we have the isentropic turbine efficiency. In the question, if you really going to see, the air is then expanded, expansion always occurs in the turbine. Okay, and passes through a regenerator which has a 75% effectiveness. Okay, so effectiveness, that regenerator is there in the what? Regenerator is a part of your what? After the turbine, this will go to the regenerator. So we are actually assuming it as a whole system as a what? Regeneration occurs in the turbine. Whole system we are considering as one. Okay, and we are actually calculating the effectiveness of the turbine. Okay, due to the process of regeneration. Okay, 75. Okay, but okay, but no, actually, okay, so this question is a little bit confusing. Don't directly consider regeneration because but the real game is here also question isentropic efficiency of the turbine also given. Okay, so in the question if it is not given, then directly consider that effectiveness of the what. So don't confuse the effectiveness and efficiency. Okay, so if it is given effectiveness of the what you call regeneration, you have to consider it differently. Okay, so first what you have to do, first to consider the turbine efficiency, then you consider the effectiveness of the regenerator. Okay, so in the question it's actually just written in the reverse way. Okay, so that's the game. Okay, I also confused, so yeah, you don't need to confuse this isentropic efficiency in the turbine. So first to the turbine, then find out the effectiveness of the what for the regeneration. Okay, get it? So first of all, the turbine efficiency 0.86 given, 86% actual by isentropic (1700 minus T4 divided by 1700 minus 1009.6). So your T4 is equal to 1106.3 Kelvin. So the exhaust is then cooled in the what? regenerated is actually cooled. So now this is the game. If you really going to understand it, it will be very good. Okay, so when there is a heat input, okay, so instead of 2 to 3, okay, so heat input in which point it will be, okay, okay, so in this exist regeneration occurs in the point 2 to x and 4 to y. Okay, okay, so yeah, because if you really going to see it, this 3 position, okay, so the regeneration always occurs in the position of what, 2 to x and 4 to y. Okay, so you can consider either of them. Okay, okay. So the effectiveness is equal to 0.75 is equal to Tx minus T2 divided by T4 minus T2 is equal to T4 minus Ty divided by T4 minus T2. So Tx is equal to T2 plus 0.75 into T4 minus T2, so which is 603.34 plus 0.75, 1106.3 minus 603.34. So Tx comes out to be 980.53 Kelvin. So now you have Tx, so now you can find out the heat input, mcp delta T, T3 minus Tx, okay, is equal to 100 into 1.005, 1700 minus 980.53. So Qy comes out to be 72306.735 kilowatt. Okay, what is the total work? Wt minus Wc Ma into Cp of gas, T3 minus T4 minus Ma Cpa T2 minus T1. Okay, which is equal to 100, 1.15, 1700 1106.735 minus 100 into 1.005, 603.34 minus 288. Okay, 36533.83 kilowatt is equal to 36.534 megawatt. This is your W total. Okay, now what is the power output or the total power? W total into mechanical efficiency into alternator efficiency into thermal efficiency. Okay, so just substitute everything and find out the P total. Okay, so yeah, so next is the thermal efficiency. Okay, this is the actual thermal efficiency. Okay, so W total divided by Q inlet, 36,533.83 divided by 72306.735 into 100. Okay, which is more or less 50%. Okay, and same thing here actually I used. Okay, 0.5. Okay, okay, okay. Okay, so yeah, This is also your answer, 50% efficiency. Okay, and I put it here, and this is also your answer. With this we are ending the section. Thank you very much for attending the section. If you have any doubt, you can ask in my question and comment section in my YouTube channel. My YouTube channel name is Sumit Sagar Hota. If you have any doubt related to your course, you can ask in question and answer forum in NPTEL. Thank you very much. We will meet in the next week 6 to 8 p.m. for the week 9 section, live section. Thank you very much. Have a nice day and good night.